Welcome to this CPD session titled Overview of PCR, which is part of the Essentials of Polymerase Chain Reaction CPD series offered by MedSkillHub, and I am a consultant with MedSkillHub. In this short introductory section, we want to set the foundation for understanding PCR as a key tool in modern molecular diagnostics. This module is accredited by KMLTTB for 3 CPD points, and by the end of the lesson, we expect you to appreciate not only how PCR works, but also why correct interpretation, troubleshooting, and quality control are so important. The main aim of this session is to help you master the application of PCR in diagnostics. Let us look at the anatomy of a master mix. At the heart of PCR is the target DNA. This is the genetic blueprint that we want to amplify. It may come from a virus, bacterium, parasite, human cell. PCR works through repeated temperature changes. These temperature changes allow DNA to be copied again and again. The first step is denaturation. Please watch the following short video. As you watch, pay close attention to how PCR amplifies target DNA through the repeated steps of denaturation, annealing, and extension. Also observe how a small amount of starting genetic material can increase cycle by cycle until it becomes detectable.
Polymerase chain reaction operates on a rigorous thermal cycle. We heat the sample to denature the DNA strands, lower the temperatures.
Primers with complementary regions bind to each other. They amplify themselves, consuming reagents and creating useless artifacts. To correct primer dimers, the primers...
I hope you enjoyed that short video. It was very informative because it helped us visualize what PCR is doing inside the reaction tube, something we cannot directly see during an actual PCR by cycle. Now, in the next part of this series, we move from theory to practice. You will interact with a PCR amplifier simulation. This simulator allows you to adjust variables, observe how amplification progresses, and see how DNA copies increase with each cycle. Pay special attention to the graph at the bottom of the simulator. It represents the kind of output commonly seen in qPCR or real-time PCR, where amplification is displayed as a curve. So take your time with the simulator, play around with it, change the available settings, observe the curve, and repeat the process. By the end, you should have a clearer practical understanding of how PCR amplification builds up and how that process is translated into a detectable signal in molecular diagnostics. Take the quiz below and let's meet in the next part of the series. Kwaheri kwa sasa.